For our next speaker, we will again be at an accelerator lab, but it'll be bringing the novel experiment and the methodology of cold atoms and atom interferometry to the laboratory. And so it'll be Jason Hogan from Stanford. He's talking about MAGIS and MAGIS 1000.
Well, it's a pleasure to be here today. My name is Jason Hogan, and I get to tell you about atom interferometry, MAGIS, and I guess change the title on you. And I'll talk mostly about MAGIS 100, which is our installation that was just mentioned, and MAGIS 1000 is sort of would be a next generation, which I'll mention on a little bit, but I'll focus mostly on the 100-meter scale that we're doing at Fermilab. Let me just start by pointing out the sort of relationship between what I'm talking about today and some of the stuff we heard about yesterday. So yesterday we heard some great talks about atomic clocks, and atom interferometry is a closely related field. Basically, the question I'd like to focus on today is how can we leverage some of these incredible gains in stability and accuracy that we heard about yesterday. So in the field of atomic clocks. So we're talking about pushing into 19 digits of precision, for example. So there's a number of, I think, interesting fundamental physics experiments we can do with this technology. In particular, I'll spend some time talking about gravitational wave detection and how it's possible to look for gravitational waves in a new, let's say unexplored frequency range, complementary to existing detectors. And then I'll also talk about sort of new, you could call them maybe hybrid sensors, or atom interferometers that take advantage of a lot of the sensitivity, a lot of the techniques, let's say, that are common already in the atomic clock community. So in particular, I've got sort of a picture here on the left of the strontium clock transition used by optical lattice clocks. This is a narrow transition with a long-lived excited state. We can take advantage of the same transition to build an atom interferometer. And so just sort of as a pictorial description, down here we've got, we heard about ion clocks yesterday and also optical lattice clocks. This would be sort of the what you might imagine for that, trapping a bunch of atoms in a standing wave potential. An atom interferometer is a closely related, but instead of trapping the atoms, we allow the atom to fall freely. And so you see these sort of parabolic trajectories in this lower picture here, showing the trajectory of the atoms. And we can divide the atom's wave function using pulses of light to split it and have it travel on two distinct paths. You see a lower path and an upper path here. And the phase shift of this interferometer, which is essentially proportional to the area spanned by these two trajectories, that phase shift can, in this case, is sensitive to inertial forces that the atom experiences during the sequence. So the acceleration in particular for this example. And so you can use this to look for small forces and other that can show up from new physics, as I'll talk about. I've got here on the right some quick pictures of this idea of gravitational wave detection, just to emphasize that you can imagine building such a detector to look for gravitational waves using both atomic clocks, which this is a picture from such a paper here using optical lattice clocks using two satellites that orbit around the sun. And then this is a picture from some of my own work, which is a similar proposal using atom interferometry. And I just want to emphasize that both of these approaches have a lot in common, and both look like an exciting, viable approach to doing this interesting science. And there's different technical trade-offs, but I think the technologies are, as I say, have a lot in common. There's a lot we can certainly benefit from the atomic clock community in our atom interferometry work, for example. So a little bit about the science that I'll focus on. So I guess I could describe a number of interesting fundamental physics tests. I'm going to focus on three areas mainly today. And for these, it's really useful to have so-called long baseline sensors. So we're talking about basically scaling up the kind of tabletop experiments that we're used to thinking about in AMO, atomic physics, towards kilometer scale instruments. And that's where this sort of MAGIS comes along in a few slides. So, so the three areas, I mentioned gravitational wave detection. There's a plot here on the right showing the strain sensitivity of various gravitational wave detectors as a function of frequency. And so this is a little bit small to read, but sort of over on the right here, there's the LIGO sensitivity curve, which is sort of above 10 hertz out to sort of kilohertz range, where we've already seen really exciting science. Sort of in the middle of the plot here is our space-based gravitational wave detectors, such as LISA, which operate in the millihertz range up to sort of 100 millihertz. But then between, there's this sort of yellow band, which is called the mid-band, between a fraction of a hertz, about 0.03 hertz to a few hertz, where neither of those detectors is covering things very well, and there's an opportunity to do some interesting science, as I'll talk about. So I guess the some of the sources that we've already seen, for example, that LIGO has detected, black hole binaries, neutron star binaries, those sources evolve in time. Their frequency increases as they get closer to final merger, and that implies that they're emitting gravitational waves in this mid-band as well. And so you could see these sources at an earlier point in their evolutionary history when they're at lower frequencies, and that has some advantages. In particular, regarding multi-messenger astronomy, which I'll say a bit about in the next slide. So that's gravitational waves. Turns out this same style detector, these long baseline atom interferometer type detectors, can also look for ultralight wave-like dark matter, which we heard a little bit about yesterday. And so these are typical models with particles with mass on the order of 10 to the minus 14 eV, sort of Hertz level Compton frequencies. And so that we can look for both scalar and vector coupled candidates, and these can show up as basically as time varying clock shifts, so energy shifts of the atoms, or as new forces. As I mentioned, we can detect by looking in particular for forces that violate the equivalence principle in a time dependent way in this case. And then finally, and this is sort of more speculative, the long baseline detectors gives us the opportunity to basically build very large atom interferometers. So long drop times allow us to split the atom's wave function by larger distances. This is a picture of sort of the existing state of the art, where you see this is data showing a rubidium interferometer, where you see sort of these little spikes are the probability distribution of the atom cloud at the moment that this image is taken, and we've been able to split an atom's wave function by over half a meter using so-called large momentum transfer atom optics. So advanced manipulations of the atom's wave function allows us to make these macroscopic wave functions, macroscopic in distance. And the idea is by making these interferometers as large as possible, both in time and in space, you can look for possibly violation, or you can test quantum mechanics in this regime where we haven't explored before. And so you can look for anomalous decoherence, spontaneous localization theories, or other kinds of modifications of quantum mechanics that might prevent you from making such a macroscopic atom interferometer. So I mentioned multi-messenger astronomy, and I just wanted to say a word or two about that. One of the motivations why we think these mid-band gravitational wave detectors are really exciting, sort of independent of the approach that one uses to make a detection. This is a really exciting range to do science. And so this is the idea of sky localization. How do you figure out where in the sky an event is sourced from? And so if you have gravitational waves, the way that LIGO works to detect location is by looking at the delay of arrival at the two LIGOs. So you can look at the travel time of a gravitational wave between the two sensors on opposite sides of the continent. But the larger you can separate the detectors, the better in terms of getting a lever arm for this differential arrival time to get a better sense of where the source is in the sky. And so the advantage of the mid-band, one of the advantages of this lower frequency sources is that the sources, they persist for a long time, in the order of weeks to months. And so in principle, that allows you to make a detection, even with a single detector that's located on the Earth, you could detect the gravitational wave for on the order of a year, so many months. And so that allow you to essentially synthesize a very large aperture. So you can basically look at the detector on these opposite sides of the sun and get, and even though you have one detector, and you look at it in differences in time, you can use that to effectively look for differential arrival time. And so that can give you a big enhancement in the ability to find out where in the sky the detector is, where the source is, which would be really exciting if you could say where it was to a small enough angle it's possible to then point existing electromagnetic telescopes in that region, so you could actually watch the final merger and detect it simultaneously in LIGO, for example, and sort of have this multi-messenger sign. So that's a really exciting motivation, I would say. So a word about how the atom interferometer detector work. It's actually very similar to how LIGO works. For gravitational waves, we imagine we have some strain wave propagating across space-time, and when it reaches the detector basically consists of a couple of inertial reference points. These black dots represent some test masses that are freely falling, and they're separated by some baseline L, some distance, and you look for a modulation in that length. And in LIGO, that's done by looking at the light travel time between these test masses, which are these mirrors in one of the arms of LIGO. And in principle, that's enough to detect a gravitational wave with the single baseline, one of the arms of LIGO, for example. LIGO has two arms. For technical reasons, it's required to suppress the noise of the laser. So this is basically a common mode suppression technique for laser noise. But in principle, one set of test masses along a linear axis is enough to look for a modulation in the length. And in fact, the atom interferometer approach that I'll outline is based on that idea, using a single baseline. So this is a little more formalized, what I was just describing. The two ingredients you need then for this kind of gravitational wave detectors, you need some inertial reference points. Some, in the case of LIGO, these are the end mirrors. You need some object that's basically freely falling and unperturbed by non-gravitational forces. And then you need some way to measure the light travel time between those reference points. So you need basically a good clock. In the case of LIGO, that's provided by this auxiliary arm. You compare the light travel time along the two arms. But in principle, if you have a really good laser, or in this case, in the case of an atom interferometer, you could potentially use the atoms themselves. And so MAGIS is the matter wave atomic radiometer interferometric sensor, and it's based on the idea of basically combining these two ingredients into one. So using the atoms both as the freely falling inertial test points, but also using the atom's internal degree of freedom as a clock in the way that we already do in atomic timekeeping, and use that as the phase reference for measuring this light travel time. And so in this sense, you can think of the atom as essentially an active proof mass, where the atomic coherence keeps a record of the laser's phase and basically avoids the need of having an auxiliary reference baseline. And so you can imagine then doing single baseline gravitational wave detection, which has some advantages, in particular for satellite missions. Right. So as I mentioned, there's on the first slide, there's the idea here is to try to make this kind of hybrid sensor where we're taking advantage of these long-lived transitions used in atomic clocks, but to build an atom interferometer. And so this is the idea of using these single photon transitions. Now, in traditional atom interferometry, using alkali atoms, it's very common to use two photon transitions, like Raman transitions or Bragg transitions, due to the lack of a long-lived excited optical transition. But in atoms that are used in optical lattice clocks, such as strontium, there are such long-lived states. So we can imagine doing an atom interferometer with a single photon transition between, in this case, these two levels here on this energy diagram, where we can expect to have 100 seconds of coherence in particular for that transition. So you have plenty of time to build an atom interferometer. And these single photon transitions have, at least in principle, a big advantage in terms of the ability to cancel the noise of the laser in the way that I described in the previous slide, using the sort of the high Q of this resonance, the fact that we're able to have this coherence persist the entire duration of the experiment. So you can see then a picture of the concept for MAGIS on the right. This is actually a gradiometer, so it's two atom interferometers, one at two different heights, let's say. So this is one. Maybe I'll show this picture first. Maybe we've got, for example, a vacuum chamber, and these two blue dots represent the two inertial reference points that we want to use to look for gravitational waves, let's say. And you can implement an atom interferometer in each of these two locations simultaneously using the same laser pulses. And then the space-time diagram on the right shows how that works. You've got an atom interferometer of these two heights, and then these squiggly lines represent pulses of light that are propagating along the baseline and interacting with the atoms. And you implement this pulse sequence, and you can build these two interferometers. And ultimately, we're interested in the phase difference between these interferometers. And that phase difference, it turns out, is encoded in the time that the atoms spend in this excited state. So in this, these different colors in this diagram represent the internal states. So the blue is the ground state, red is the excited state. And it turns out that the phase shift, which is given here on the lower left, is proportional to the energy splitting between the atomic levels. So that's omega A here, the clock energy, and the light travel time back and forth across the baseline. That's 2L over C. And so if the baseline, for example, varies due to a passive gravitational wave, that's a change in L, then you would see that delta L as a time-varying differential phase shift between these two atom interferometers. But as I mentioned, this sort of is a 2-for-1, right? So you can look for gravitational waves, but you're just as sensitive to variations in the clock energy omega A. And one way that can vary is due to a coupling to an ultralight wave-like dark matter field. And so if there's such a field, then it would cause some energy shift, which we would also be able to see as a time-varying differential phase shift. So in the same machine, you basically can look for both of these effects simultaneously. So let me say a word or two about the state of the art. As I've said a few times, these are to really get into the interesting science range, we need a long baseline. What does that translate to? Kilometer scale instruments. So we need to look for basically something similar in size to LIGO in order to hope to see gravitational waves. The current state of the art with atom interferometry is sort of summarized here at a number of facilities around the world. There are these 10-meter vertical drop towers. And so, for example, this one here at Stanford, there's a 10-meter vacuum chamber with an atom source at the bottom, and the atoms are launched in this and fall for a couple of seconds while we can do it atom interferometry. There's also a number of other experiments around the world. So a recent work in Hanover to build a similar scale 10-meter device. There's a machine in China. And then recently in the UK is this Aeon proposal, which has now been approved, I should say, and is beginning to be designed, which is another 10-meter scale machine with ambitions towards making 100 meters machines in the near future. And then I should also mention in my group at Stanford, we're working on another 10-meter machine, but this time using strontium atoms. The existing Stanford tower uses rubidium, and the strontium atoms, once again, are motivated by the existence of these clock transitions. And so we want to demonstrate that we can do the same sorts of experiments that have already been done with alkali atoms using these clock transitions. And so we built 2 strontium atom sources, and we're now in the process of building this 10-meter scale vacuum chamber where we'll have atom sources, one sort of halfway up and one at the bottom, that'll allow us to make the gradiometer that I described in the previous slide. This is sort of a prototype for the MAGIS experiments that we're excited to do. So there's actually a number of groups around the world that have started to extend from the current state of the art to long baseline sensors. So this is kind of a selection of those. And so, as I mentioned, my work is on MAGIS, and I'll say a word about that on the next slide. But I want to make sure to emphasize that this is there's sort of it's an exciting time right now where, as I said, there's lots of groups that are starting to do this. So I think people are excited about the science opportunities here. So in France, there's NIGA, which is a horizontal machine with sort of a couple 100-meter long vacuum chamber with a number of atom sources along the length that aims to do gravitational wave detection and similar science. I mentioned Aeon in the UK, which is designed with an emphasis on being collaborative with MAGIS and essentially acting as another detector where we can cross-correlate data between these 2 devices on opposite sides of or separated by a large distance, which is great for things like gravitational wave science, where you want to have confirmation that the detection is real. And then in China, there's the Zyga effort where they're building vertical and horizontal vacuum chambers in a mountain with a very ambitious proposal to do the very similar science. So I guess the takeaway here is lots of effort going on in a number of areas, and I think that there's a lot of also enthusiasm in the community that we form sort of this sort of consortium that you have seen in LIGO and Virgo, where it's really helpful to be able to compare data across these different experiments. And so I think that that would be really amazing if such a thing could be done with this atomic technology as it progresses, and certainly all the different efforts can learn from each other. And so so let me talk a little bit about MAGIS. So MAGIS 100 is we call it a detector prototype. It's a 100-meter scale machine. It's a prototype for future kilometer scale machines, which is what you would need, as I said, to do gravitational wave science. So MAGIS is to be installed at Fermilab. There's an existing 100-meter vertical shaft from one of the neutrino beam experiments that we're going to take advantage of and install an atom interferometer along the length. We're going to use 3 atom sources, strontium atom sources, one at the bottom, one at the middle, and one at the top. And this, we'll be able to do the 3 science areas that I mentioned before: gravitational wave science, ultralight, dark matter, and also extreme quantum superposition states, where we're hoping to drop atoms for many seconds and aim for larger than meter scale wave packet separation while the atoms are in free fall. I should say this is a collaboration of 9 institutions, so it's really sort of learning how to move from sort of the kind of atomic physics scale, not only in size, but also in terms of collaboration, where, at least in my experience, it's usually smaller groups or a single group worth of effort. And here, where it's really helpful to start having groups from a number of institutions participate in a larger scale experiment. So we're really learning from the particle physics community, and the participants at Fermilab have a lot of experience with managing these larger scale collaborations, and that's something that is I think important for moving these scaling up these detectors ultimately to the size that's necessary to do a full-scale gravitational wave detector, for example. So here's some sort of schematics of what MAGIS 100 will look like. This is the MINA's access shaft that I mentioned before. It's a 100-meter vertical shaft. You can see sort of a little bit of light at the bottom. We're going to install the atom interferometer right along this wall here. And you can see kind of a schematic of that in the middle, where the installation in the shaft is. You can see the top of it here. We have the laser lab nearby, where we send light from high-power laser system into this vertical vacuum pipe and send it down to the atoms. There are 3 of these atom sources located at, as I said, 3 points along the shaft. And MAGIS 100 is based on a modular design, so this is one of the modules, and they're about 6 meters long. Each, we stack a bunch of these end to end, and these each are basically a vacuum chamber with magnetic shielding and other support systems, and we can then install them end to end to build the whole machine. And that effort the design is quite mature now, and we're hoping to start building over the course of the next year and installing. So in terms of sensitivity, I've got both gravitational wave and dark matter coupling shown on this slide. So first off, on the left, the gravitational wave sensitivity, what can you do with MAGIS 100? So MAGIS 100, as I said, is a prototype machine. It's not long enough, likely, to detect gravitational waves. We expect that to require a kilometer scale instrument, but it's possible to do a lot of interesting work on gravitational wave science, basically in the spirit of understanding how to build larger detectors and learn what would be required to ultimately scale up. That said, the sensitivity is shown here, LIGO on the right, LISA on the left, and then you can see in blue in the mid-band range where MAGIS works. This top line here is assuming current state-of-the-art effort in terms of, in particular, the atom optics, how we split the atom's wave function using multiple pulses of light. And current atom flux numbers that have been demonstrated. But we actually think there's a lot of room for improvement in that, even at MAGIS 100, at this 100-meter scale, where we can enhance the sensitivity both by using higher flux atom sources to reduce shot noise and increasing the beam splitter momentum to increase the space-time area of the interferometers, and also potentially incorporating quantum entanglement to reduce shot noise. So all those together allow you to, in principle, push this down by several orders of magnitude. So we see MAGIS 100 really as a development effort, not only to demonstrate scaling up from 10 meters to 100 meters, but also to try to implement some of these enhancements that are needed to get down to the sensitivities we imagine are possible. In the dark matter space, you can see an example for this is a coupling to the electron mass on the right here, compared to existing bounds. You can improve that by 1 to 2 orders of magnitude with reasonable parameters that we think we can get sort of with current state-of-the-art results. And then also this is an example of a B-L coupling. This would be a differential force measurement. We would use 2 different isotopes of strontium for this measurement, and where you can see a large range where we can improve beyond existing bounds. I won't spend too much time on this, but one of the directions carrying on after MAGIS 100 is to scale up to a kilometer baseline on the Earth, where we have you can certainly find mine shafts that are vertical mine shafts with several kilometers of length that could be used for that. But another exciting opportunity would be to do this in space, where you have the flexibility of using a much longer baseline. And so this is a concept for that we've thought a lot about, where you can use two spacecraft separated by, in this case, for this example design, over 10 to the 7 meters baseline, and using sort of physically realizable parameters for the atom interferometry, you can get really exciting sensitivities I'll show on the next slide. This takes advantage of a so-called heterodyne link concept, which is analogous to how LISA works, where you basically synthesize the baseline measurement between the two atoms by using sort of an optical ranging between the spacecraft combined with the atom measurements. So this is kind of a summary of where this can go in terms of gravitational wave sensitivity projecting into the future, both for terrestrial and space-based gravitational wave detectors. So the same plot, once again, showing LIGO on the right, LISA on the left, and the midband here. And what you can see is that for a kilometer scale instrument in green here, you can get to really exciting sensitivities that are enough to see sources that have already been seen. For example, this red curve was the first black hole binary that was seen by LIGO. And then in space, it's possible to do quite well. So this black curve shows a so-called broadband sensitivity curve. It's also possible to increase the sensitivity using resonant detection. This would be called dynamic decoupling sequences. Dynamic decoupling sequences in the atomic clock literature, where you do multiple pulses at a fixed frequency to look for a narrowband response. So that's these dashed lines. You can sort of zoom in on a particular frequency range and get down to this brown sensitivity curve. So there's a lot of potential for gravitational wave science here. I want to say that there's an important background called gravity gradient noise, shown here in orange, which probably limits terrestrial detectors below a fraction of a hertz, and that's where you really would want to go into space. Okay, so the development path here, I think that there's a number of areas of a number of technology areas where we want to push. So this chart sort of shows where we think things can go. So current state of the art is a 10 meter scale using sort of roughly 100 h-bar k of momentum transfer in terms of how far we can split the atom's wave function. That's what's been demonstrated already. And so there's a number. So that's one of the areas where we think we can make a big improvement. Increasing the large momentum transfer atom optics by a couple orders of magnitude would give you a factor of 100 sensitivity improvement in gravitational waves. And then the other way forward would be, as I mentioned, increasing the number of atoms and using quantum entanglement, which both we see as potentially giving you up to a factor of 10 each in the future. And so there's basically a lot of work to do to sort of reach these goals, but we think this is what's physically possible in a future detector. I think I'm pretty much running out of time, so I may have to cut this short. I don't know. I'll maybe spend a minute or two because I wanted to mention, since it's such an important part of the development effort, I want to say a word or two about large momentum transfer atom optics and some of the work my group has been doing on that. This will just be a quick summary, though, given the time. Okay. So we're talking about using strontium atoms to do MAGIS-style detectors where we have these single photon transitions, such as the Strontium clock transition. And there's actually another, so that's primarily motivated by the reduced coupling to laser noise that you can get in a MAGIS style gradiometer. But there's another advantage, it turns out, in terms of the number of pulses that you can apply in a large momentum transfer atom interferometer. In conventional alkali atoms, where we do these 2 photon transitions, typical the tunings from the excited state are limited to sort of tens of gigahertz, and that sets a scale for how much spontaneous emission loss you get from this far detuned state. In the sort of the equivalent limit in strontium is really exciting because the separation to the nearest excited state where you have spontaneous emission that's substantial is hundreds of terahertz away. And so there's a big suppression in the spontaneous emission rate. And so, the current state of the art, as I mentioned, is about 100 sequential pulses limited by spontaneous emission. We see a path forward towards many times larger than that. At least theoretically, you could do hundreds of thousands or up to 1 million pulses if that was the only limit. So that's a really exciting direction. And so we set out to test this out last year, and we're working on actually the intermediate line transitions to the triple P1 state. For the experts, this is sort of not the long-lived state, but has sort of kilohertz line width, which is sort of a nice intermediate range for testing these single photon transitions. And we did a large momentum transfer sequence where you can see a sequence of pulses here on the bottom, and we can split the atom's wave function by a larger and larger amount depending on how many pulses that we were able to do. And just to summarize, this was the first demonstration of a large momentum transfer atom interferometer using a clock transition that we're aware of, and we were able to push out to over 100 h-bar-k, which actually exceeded the state of the art by any other method. So it's the first demonstration, but it worked. It was quite effective. So we're able to actually set a new limit, even though it was the first time that had been done. So that's really promising. We see avenues towards moving this out by another factor of maybe 10, hopefully in the near future. And we also did a gradiometer, which is sort of a differential measurement between 2 atom interferometers, very much in the spirit of what MAGIS would be based on, and that worked as expected. So let me end by just outlining sort of what I see as a number of challenges and open questions. First off, we're scaling right now from 10 meters to 100 meters, and so we're learning a lot in that process. There's obviously going to be a lot of challenges moving from 100 meters to a kilometer scale. We're hoping that what we learn now will be useful on that next push. For space-based detectors, there's a huge whole other topic there about how do you qualify this technology and develop it so that it's space ready. How do you include quantum entanglement, spin squeezing in these sensors is still an open question. It's very, very exciting, but very challenging. There's a need to develop higher flux atom sources if we really want to push down to these sensitivity levels. Pushing out to 1,000 h-bar-k of momentum transfer in atom interferometry is something my group is really very interested in focusing on. And as I mentioned, some of the gravity gradient noise issue, I didn't really talk about it much, but there are ideas for how one might mitigate that we could work on. So let me end there and just want to make sure to acknowledge all the different institutions, as I said, on MAGIS 100 and all the folks that are involved with that. And so thanks a lot for your time.
Thanks. That was extremely interesting. So as before, can we start by raising hands? Who has a question? Okay, Jake.
Jason, thank you so much for that. Really interesting and great progress, obviously, in not just taking this idea forward, but trying to really implement some of the key ingredients. I guess, speaking very simply, it seems a lot like what you're describing for MAGIS is really a measurement system for the gradient and acceleration. Am I missing something?
Yeah, that's you can absolutely think about it as a differential acceleration measurement. If you think about the atom interferometer in a conventional 3-pulse atom interferometer sequence, it's an accelerometer, and if you take the difference of that, you'd be sensitive to gravity gradient, and so that would be like a DC effect. You would see the difference in height, difference of gravity and height. And so on some, you can talk about gravitational waves, for example, in a number of ways. In one way to talk about it would be a time-varying gravity gradient. That's one language you could use in a particular gauge. So we're looking for time-varying differential accelerations, and then I would extend that further for the resonant sequences, or in a dynamic decoupling sequence. There you're not sensitive to the acceleration, but rather just more higher derivatives, if you like, of the motion. Ultimately, looking at you can really zoom in on a particular sinusoidal oscillation, if you want, of the differential motion.
So then my follow-up question is well, one, what is your etvosh per root hertz you're projecting for the next generation of MAGIS?
Yeah, that's right. So I guess I'm a little hesitant to give the numbers. Etvosh parameter is the ratio of the differential acceleration over the mean acceleration. So this is the parameter you use to characterize an equivalence principle test. And the big difference between MAGIS and sort of a DC equivalence principle test is we're really focusing on time varying, so oscillatory differential accelerations. It's a lot harder to make a DC measurement than an AC measurement in some ways. You know, for example, if there can be a differential acceleration that's fixed in time, it would, you know, look like a violation of the equivalence principle, but wouldn't be in our target frequency range. So we wouldn't have to worry about systematic errors that are slowly varying. We could focus on systematic errors in our range of interest. That said, our differential acceleration can be, you know, quite good, so better than 10 to the minus 15 g, just as a rough idea at a particular frequency. If for these sort of extreme numbers that I gave for MAGIS, where you're talking about multiple seconds of drop time, essentially. I don't know if that answers your question. So I'm not trying to dodge. Just we really don't want to do a DC measurement because that is much harder. So for example, if there's a magnetic field background, for example, that causes that will cause the energy levels of the atom to shift, and that might be different at the two atom sources, and that would look like an effective differential phase shift between the interferometers. But if it's constant in time, it's not varying in our target range, then we can reject that. So that makes it a lot easier to design the apparatus by focusing on.
Okay. So to read it back to you, what I heard you say is you're targeting a 10 to the minus 15 over about 10 seconds of integration time for the sensitivity of the individual interferometer in the setting.
So that would be for a single drop time on the order of several seconds of drop time. Yeah. Mm-hmm.
Yeah.
So per shot. Yeah. Mm-hmm.
That's really impressive, obviously, given that state-of-the-art atom interferometers are more at 10 to the minus 12.
Yeah, so the larger drop times give you a lever on that sensitivity, and the large momentum transfer atom optics that we're talking about also scale up that sensitivity. So it's a combination of these two. So state-of-the-art equivalence principle measurements using something like 10 h/k atom optics.
You're looking for a factor of 100 by going to 1000 h/k and a factor of 10 by longer drop times.
You can do, yeah. So I'm being a little bit rough here because there's a range of differential accelerations that we hope to get to these dark matter sensitivities. But yeah, that's the right idea. A couple orders of magnitude in each of those areas.
The reason I ask all these questions is because what you've described is something that's going to fall under export controls. And so I'm curious, you know, what the path forward is there anyway.
Yeah, so right. So so I guess maybe the military applications are a little bit unclear for defense applications for a 100-meter installation. But yeah, I think that the sensitivity is pretty exciting. And we I guess we're mostly focused on these fundamental physics applications. So I don't anticipate that to be too much trouble. And I guess, as I said, I really hope that there's a good international collaboration where we can share technology ideas in this area. So hopefully that doesn't come in.
Thanks.
Okay, next I believe was Lance.
Hi, thanks a lot for a very interesting talk. This is probably a naive question, but I noticed that your frequency range was more or less dictated by the drop time. And if there were any interest in going to lower frequencies, is there a way to, you know, maintain the phase information by sort of juggling, that is, tossing atoms at different times and carrying it across? And then I would need to understand what's the gravity gradient noise in terms of the, you know, you said it was cutting out that region. Could you comment on that, please?
Yeah, sure. So that's great. Yeah, absolutely. I think that you can certainly imagine doing these sorts of juggling schemes. It's I guess it's always important so the idea is certainly sound. We've thought a little bit about that. The challenge is whenever you touch the atom, you have to worry about how that influences the measurement. And so for example, the limit of juggling would be to just confine the atoms. You could trap the atoms in some potential, but then if to the extent that you put the atom in a trap, the atom is no longer an inertial reference, right? The idea here of having the atom be freely falling is really critical for how the sensor works. It's only subject to gravitational forces if we've done a good job, right? So really want it to be a freely falling particle. And so if you're trapping it, now what the motion of that atom is dictated by the stability of whatever the trap is. And so this is really, you could say, a big difference between an optical lattice clock and an atom interferometer, for example, where the lattice clock, you're rigidly connected to the lattice and therefore to the rest of the of the world, and so you no longer have an inertial reference. And so
I wasn't talking about trapping it. I was just talking about tossing them at different times and trying to straggle and carry the
absolutely. No, forgive me. I was just thinking that a juggling sequence is somewhere in between in my mind, where you're periodically pulsing on you're applying some force periodically to toss the atoms up again, and so if you do that in a clever way, you may be able to do it without perturbing this inertial reference idea. But you have to be really careful. That's all I'm saying. So that would be one constraint. But yeah, I think the idea is really exciting. In terms of going to lower frequencies on Earth, you mentioned gravity gradient noise. So this orange band here is a rough estimate of what that is. It's just very site dependent, it turns out. So what this is a freely falling atom is exciting because it's decoupled from vibration noise to a large extent. So if you think about LIGO, there's a tremendous effort to decouple the test masses from the Earth using isolation stages, and you need to do the same thing here. But if the atom's in free fall, you don't need a pendulum, right? It's just decoupled. And however, there's still an indirect coupling, which is the motion of nearby mass due to seismic noise. The dirt is shaking around. That can couple to the atom via gravity, and you can't shield that. And so that's what gravity gradient noise is. It's just time varying Newtonian gravity due to shaking mass near the Earth, near the source from the Earth, and near the atom. And it would be difficult to go below probably a fraction of a hertz based on naive projections. Now there are some ideas for how you can possibly mitigate that, and that's actually motivates why MAGIS uses 3 atom sources. So I showed this picture here. We have a source at the bottom, middle, and the top. In principle, you only need one at the top and the bottom. That's the MAGIS concept. The reason we put one in the middle is to potentially reject gravity gradient noise. And here, the idea is the Newtonian forces vary like 1 over r. The potential varies like 1 over r, or forces like 1 over r squared. So there can be a position dependence associated with a Newtonian background, whereas a gravitational wave very much is a planar excitation. And so, in principle, you could imagine looking for curvature across the baseline, or maybe if you had an array of many atom sources along the length, you could look for higher derivatives of this and use that to correlate those sources with the gravity gradient noise and subtract it, measure and subtract. And so that maybe let you push the gravity gradient noise down by perhaps a factor of 10 or so to get to slightly lower frequencies. But to go much lower, it's going to be difficult on the Earth, and you probably want to go into a satellite mission.
Okay, we've had a couple of people patiently waiting. Luke Caldwell is next, I believe.
Hi, thank you for a very nice talk. Mine's kind of a technical question. I was wondering whether you could say a little bit about vacuum. How good does the vacuum need to be, and is that challenging in a 100-meter or a kilometer long tube? And I'm also wondering whether you need vacuum in between the atom sources.
Great question. Yeah, so the vacuum that we're targeting is sort of low 10 to the minus 11 millibar range. So which is kind of typically what we have in our 10-meter scale machines. Extending that to 100 meters is challenging, but the team we're working with at Fermilab has experience doing exactly that in a particle physics context. So and they assure us that they've done it before and that it's relatively straightforward. And essentially, technically, we'll have ion pumps every 5 meters basically to help ensure that. And then your second question was about do you need vacuum between the atom sources, and not in principle. So if the atom sources are localized to certain regions of the vacuum pipe where you have really good vacuum, and then the vacuum was not so good in other areas, that you could get away with that in principle. In MAGIS 100, we're trying to make the entire 100-meter shaft at this sort of 10 to the minus 11 torr range, and that's to give us sort of 10-second time lifetimes or longer, so we don't see a substantial loss of atoms during these long duration free fall times. You can imagine the most ambitious experiment you might do would be to launch atoms from the bottom of MAGIS, and you can imagine launching the entire height. So launching the atoms from the bottom, having them travel up and down, and that would be over a 9-second free fall time. And so we want vacuum that would support that. Scaling up to a kilometer, it's not clear that you'd need the whole kilometer machine to be that big, and you might be able to get away with some regions where the pressure was not as good.
Cool, thank you.
Okay, let's see. Earlier, Tanya Rousey had her hand up. Tanya, are you still there, and do you still have a question?
Oh, sure. But I think it was sort of answered in a previous question. I was just going to ask why gravity gradient noise isn't a problem in space, but I think that got covered. But if you want to expand on that,
yeah. So it actually it is somewhat still a problem. So the idea is any shaking mass can cause a time varying acceleration that you have to worry about. And in space, the advantage is you're far away from the Earth, so you don't have to worry about the seismic noise of the Earth. But the spacecraft itself exerts a gravitational force on the atom and that, or on any inertial sensor that you would have. This is the case in LISA as well. And so you have to make sure that the sort of any anomalous motion of the spacecraft itself is not inertial. It's subject to all sorts of non-inertial forces potentially, and those perturbations can cause differential noise on the atom interferometer in this case. And so you have to make sure the satellite's not moving too much. It looks like it doesn't require extremely good control. Like you may be able to get away without using a drag-free control system, for example, using a MAGIS style detector, which would be a huge advantage over other like LISA-like concepts where you need drag-free control. But still, the motion of the satellite itself is the analogous effect.
Good. Following up on the space question, what about other aspects of the space environment? For instance, charged particles. Are they a problem at these levels?
Yeah. So I guess the concern can be, well, I guess there's charged particles are, we have the atoms in a I guess I have a picture of this, but in a vacuum can to keep them protected from, maybe I can't find the slide, but the idea for this would be to put the atoms inside an enclosed vacuum chamber where they're protected from many of the, protected from the solar wind, for example. It's protected from light from the sun, and so we think it's possible to keep the atoms sort of in a meter scale region inside the satellite to get away from that. In LISA, there's an issue where you have to worry about the fact that the proof mass may build up a small charge. There's active compensation of the proof mass's charge to servo it to zero, because if you have a charge, obviously that's a potential electromagnetic force that could perturb the test mass. Atoms are nice, neutral atoms are nice, and that's not a concern. If an atom were to take on another charge, we would have lots of ways to reject that. It would no longer be a strontium atom. It would be an ion now or something, and so we wouldn't worry about that. So proof mass charging is not an issue with an atom interferometer.
Good, thank you. Okay, we're now into our more general discussion period. So anyone who wants to raise questions having to do with the two talks we just heard, or for that matter, anything else. Yeah, remember, we heard several people. Yeah, good. Anna Maria.
One quick story. So do you mind telling us about, you're measuring entanglement, so introducing spin squeezing or squeezing in the system. You can tell us a little bit of any direction or how you are planning to do so. Is this in the short term, or is really in the long term goal, or what are the, yes, what is the possibility that the spin squeezing could help or could be implemented?
I guess that was a question for me, right?
Yes.
Yeah. So I think the possibilities are really exciting. I didn't mean to downplay it too much. I guess the idea is that we'd hope to leverage a lot of the work that's been going on in the community already in this area. So as you know, the state of the art has been in rubidium atoms. There's 20 dB of spin squeezing has been shown in metrologically relevant squeezing, I should say, and so. Effort right now at Stanford is towards basically transferring those same techniques, which is this is like a cavity-based squeezing demonstration in the Kasovich group, would be to transfer those that approach to the strontium system.
Yeah, but in the cavity you cannot free fall. So, and then as you are going to scramble the phases if you are not completely uniform. That's the problem. And if you
well, I think there are. I think that the idea would be to still be able to do free fall, and so that's actually work I think ongoing is to show that you can use use a cavity squeezing protocol and then take the atoms and let them fall out of that and then still make the same MAGIS scheme I've been describing with freely falling atoms and taking advantage of the entanglement you can get in the cavity. But I really can't say too much about how that will actually look in MAGIS, like where we would need to put the cavities in the atom source or as part of the detector presumably. So it would require a redesign of how the atom source and detection area works for sure, to incorporate the cavity where the squeezing can take place. So that's why I think of it as a little bit more longer term, but the idea I think is compatible with the sort of freely falling atoms that I described.
Okay, great. And the other quick question is, well, in the clocks, one of the major complications that we have, well, again, this is trap, this is not in free fall, this is trap, is that even though the lifetime of single atoms can be, well, depends on, in 3P1, I think it's microseconds, I mean, it's 7.5 kilohertz. But we find that collisions between the excited states relax the sample very quickly. So that's why you had to, the 1D lattice was the ideal case when you have one atom per side. So do you think that this type of, or you're going to operate in such a dilute sample that this is not a consideration, or do you think that at some point it's going to be also a limitation?
That's a great question. I think it's something that we thought some about, but it is definitely an open question since we haven't done for long times. But the idea would be to operate at a very dilute sample where the collisional dephasing would be reduced. So that hasn't been shown at the timescales that we're interested in. But the rough estimate suggests that wouldn't be a driver. So I guess that's one of the things we hope to show in the both with the 10-meter machine, with strontium atoms that our group is building now, and then eventually a MAGIS. But yeah, so basically use a low enough density where collisional shifts. So it's not just collisional dephasing that we worry about, but also you get a shift of the clock energy level that due to the mean field, and then you would worry about time-varying density could cause time-varying phase shifts that would show up as a systematic error, maybe in the frequency band of interest. So if every sample had a different number of atoms, that's very dangerously in the frequency range we're trying to sample, right, once every second or so. So it's a real concern. But the idea would be to use, mainly to mitigate by using very low density. And so in particular, the cooling protocol would involve, after laser cooling and most likely evaporative cooling, a matter wave lensing phase where we actually intentionally expand the cloud and then collimate it at a low density. So that would be it, without decreasing phase density, but decreasing velocity and increasing size, which is good for two reasons, right? Then you're expanding less quickly and you're less dense.
Mm-hmm. Okay. Well, looking for it could be very exciting. Let's see. Yes, thanks. Mm-hmm.
Yeah, more questions and discussion. Great talk. I do have a question. You talked mostly about gravitational waves in terms of the physics or astrophysics applications. What about kinds of new physics? I think we'll probably hear about that from Peter Graham this afternoon, or sorry, after the break. But can you say anything about new physics capabilities of your devices?
Sure, absolutely. So I mentioned maybe not enough about the prospects for looking for scalar and vector coupled dark matter candidates.
Yes,
and so
right.
that would be new physics that we can see even with MAGIS 100. So MAGIS 100 is long enough to see in a new parameter range that hasn't been explored these potential candidates. And I guess. So those fall into two areas, right? There's at least in MAGIS, we can look for two mechanisms. One would be energy shifts, so it changes the clock energy level. But the second would be any sort of differential force that would be it would vary with the isotope. So we plan on using 2 different isotopes of strontium for some of these measurements, co-falling in the same ensemble, and looking for, in this case, time-varying EP equivalence principle violating forces. And so, equivalence principle measurements are really great for generic tests, for fairly generic tests of sort of new physics, because you can look for anything that a lot of things. Most new physics would tend to violate the equivalence principle, and so you can look for, in this case, time-varying effects due to maybe a dark matter field.
Right.
And then I mentioned also the long base, the sort of the long duration atom interferometers and the large wave packet separation. Also, that would be new physics as well. Certainly, if we saw any breakdown of traditional quantum mechanics, that would be quite novel. So basically, looking for studying T-coherence and anomalous T-coherence in sort of macroscopic or human scale atom interferometers.
Right. I guess I would call that the principal equivalence for quantum entanglement or something like that. Very worthwhile to test, I think.
Great.
Okay, who else has a question, comment, suggestion, grand vision on any subject?
Yeah. Can you guys
Josephine.
hear me? Yes.
Yeah.
So how would you test what you just mentioned, decoherence?
Well, I guess the idea would be by operating the atom interferometer with a duration of over 5 seconds, let's say, and by splitting the atomic wave function by distances of over 1 meter, we would be operating in a regime where a superposition state that's persisting for a very long time or over a long distance in a regime that hadn't been explored before. And so textbook quantum mechanics says nothing interesting should happen, and we should just be able to see straightforward quantum interference, constructive and destructive interference of the matter wave packets over such long durations and distances. But potentially there could be new physics where quantum mechanics breaks down. So, for example, spontaneous localization theory, where there's some probability that the atoms, that such a superposition state would just decay and localize into one arm or the other. And in that case, you wouldn't be able to see interference anymore. So it would be just a loss of the interference signal, an anomalous loss of the interference signal. Now, there are, of course, many classical ways that can happen too. And so we would be able to basically put a bound. But if we did see something anomalous that we couldn't explain via another mechanism, it would be an interesting direction to pursue further.
Oh, thank you.
Oh, okay. Holger, you have your hand up. Go ahead.
Sorry, I had to unmute myself. This was a wonderful talk, Jason, and I'm particularly excited to hear about the recent results from your lab. But I had a question about the proposed gravitational wave detector. It is my understanding that getting a gravitational wave sensitivity along of about 10 to minus 17 per root hertz over 100 hertz baseline essentially amounts to reading out atomic clocks given by the strontium clock transitions at a level of 10 to minus 23 or 24 per root hertz. And this exceeds current capabilities drastically. So I wonder what your thoughts are. Maybe my estimates are off.
I'm not sure about those numbers. But let's just focus on a point of agreement is certainly that the sensitivity we're talking about is beyond state-of-the-art atomic clocks. So if you take state-of-the-art atomic clocks and translate that into gravitational wave sensitivity, we would need to go beyond that. And so yes, this is definitely part of the development path I was describing on that last slide. And so the areas where we hope to improve are primarily in the area of large momentum transfer atom optics, where we can get an enhancement there, and in terms of flux and squeezing. So I guess with the difference between a clock and MAGIS is, we're not as concerned with accuracy. So there's stability and accuracy. And so we're primarily talking about stability here, increasing, if you wanted to make the analogy to a clock. And so sort of DC error in the clock frequency is something, that wouldn't perturb the measurement that we're talking about. We'd be more sensitive to things in the frequency band of interest. So yeah, so that's where we aren't totally analogous to a clock, and that makes things a little bit less ambitious. But no, it's certainly there's a number of orders of magnitude of improvement between where we are now in atomic clocks and atom interferometry and where we would want to be. But as we heard yesterday, there's exciting prospects for even clocks getting to 10 to the minus 20 in the relatively near future. And I think that that those sort of improvements benefit the atom interferometer case as well. So I guess, but yeah, so I think I might take issue with exactly the number, or maybe we could work it out. But I think there's 3 to 4 orders of magnitude improvement that we're hoping in the atom interferometer to go from state of the art to what we would need. So that's certainly true.
That's fine. We're supposed to be audacious at this meeting. Let's see, we're just about out of time. We do owe you a break. Lance, do you have something very quick, or?
Yeah, I think it's pretty quick. It's just when you're making the dark matter, dark matter bounds or measurements versus gravitational waves, is that happening at the same time, or do you have to run in a dedicated mode for the 2 cases?
Yeah, it can be in the same mode for one of the 2 dark matter sensitivity directions that I mentioned. So for the energy shifts, there it's the same mode where we're operating the gradiometer with a 100-meter baseline, and that's acting as a gravitational wave detector and as a dark matter probe. There's another style of dark matter probe we can do where we use 2 isotopes co-located from a single atom source. And that would be not sensitive to gravitational waves, so you can alternate between those 2 modes if you want to look for sort of equivalence principle violating differential forces. That would be, but if you're operating gravitational wave mode, you are looking for actually a wide variety of dark matter couplings that shift the energy levels.
But are you looking at the differential between the 2 groups, or are you just looking inside one of the groups for the?
So for the in the gravitational wave detector mode, you're looking for, it's not differential with isotope. So this is really a shift of you're using a single isotope in both locations, and the mechanism there is you're basically, since you're interrogating these 2 atoms separated by the baseline, you are interrogating the energy level at slightly different times, differing by the light travel time. And so if a dark matter field that couples to the atom is oscillating in time, the sort of instantaneous energy level of the atom will be different at the time of arrival of the light in the 2 cases. And so you see that differential in the phase. So that signal you can see with the gravitational wave detector mode. If you want to look for a differential force that couples differently to the isotopes, then you need to use 2 different isotopes at the same time.
Thank you.
Well, Jamie, and all speakers, thank you very much. 2 great talks. And so we're on break until the top of the hour, or 10 a.m. California.